well, it gives me a great pleasure to have our second speaker from another continent, from Europe. So our second invited speaker, and please correct me if I say your name incorrectly, Ana Fontcuberta Morral. She's an associate professor at the Institute of Materials at l'École Polytechnique Fédérale de Lausanne. The title of her talk is Compound Semiconductor Manufacturers, Synthesis, and Sustainability Aspects.
Thank you, Anna, for being here with us, and please welcome with your talk.
Thank you very much for this kind introduction. And thanks a lot for the invitation here today. I think we're dealing with an important topic, which is renewable energy. And also, it's very important that we get women together to celebrate excellent science too. We've seen that this COVID crisis has affected especially women and women with children at young age. So it's important that we get our science out too. So I'm going to talk about compound semiconductors. I'm changing a bit topics, inorganic semiconductors, and I'm going to talk about one of the things that have been worrying me a bit is sustainability aspects. And so the elements that we use, are they available enough or not to make the solar cells available for everyone? So I'll start with a question that we all share here, and it's, we want to all answer in this symposium, can we conveniently use the energy of the sun in other ways than just photosynthesis and for the generation of electricity? And as a scientist, and I asked this to my students too, is as a scientist, what are our roles in this? And our role is to explain to the population about global warming and how we use energy in an efficient way, but also can we find new ways to efficiently use this energy? So as I said at the beginning, one of the issues that has been worrying me a bit is the material selection. So we do very good science, outstanding science, and we find new ways of converting solar energy into electricity. But what will be the outcome? If we find something that is very useful, can we expand it that everybody can have these devices on every roof? And when we discuss about this, we come to material selection and what are the materials, if there's enough of these materials on the solar, on the Earth crust. So here I select materials, and what you see here is the potential for the material to produce electricity given the resources. And you see here, you have here the US annual electricity use and the world use. And you see that for gallium arsenide, given the current production, we are just close to what the world needs in electricity. And there's very few range of potential given the resources we have. If you look at zinc phosphide, which I'm going to talk at the second part of my talk, you see that in this material, the potential is much higher, and it doesn't look that we're going to run out of it in the near future. Another way of looking at this data is here. So in this paper, the scientists, they calculated an index related to the material extraction potential and to the potential in producing electricity. And here you have most of the inorganic materials to produce solar cells. And basically, you want to be in this quadrant here, to be in a material that is easy to extract and also has a potential to produce a lot of electricity, given the resources we have. So I'm going to talk about gallium arsenide and zinc phosphide. And what I'm going to talk at the beginning is how we can bring gallium arsenide that it's not in the positive side of annual electricity potential to here by just showing how we can use the resources in gallium arsenide a bit better. And then in the second part of my talk, I'm going to talk about these new materials in phosphide and how are the good ways that we can find to produce it in a high quality so that we can use it in solar cells. So just a small reminder about how we also select materials. So if you have a single band gap solar cell and you need to match the band gap to the spectrum of the sun, and this gives you this curve here, the Shockley-Price limit, and it tells you that these are the materials that you are mostly used for conversion. So in blue, you have materials made of elements. Some of the elements are not abundant, and in orange, you have materials that have elements that are highly abundant. So by trying to improve gallium arsenide, which is not made of gallium that is not very abundant, I got inspired by these two people that you see here, Albert Borman and Harry Atwater, that decided to look into the photonics of materials, because they thought there was a lot of range in which this could affect the output of the solar cells and how this could improve really the efficiency. So I got inspired by these concepts. Some of their papers are here in which they explained how light management can be utilized in very smart ways. Like you see here, you can use a kind of grating couple effect to just change the momentum of the light, so that the light, instead of going through the layer, can just change it and go be excited in this perpendicularly to the incident way. And so this is a way that you can absorb light very well. So this is an example of ways of using photonic concepts in which you can increase the light absorption. So I got inspired with this, and I thought, is there a way that you can use a different kind of structure that can also give enhanced light absorption? And so the question went into using semiconductor nanowires. So nanowires are filamentary crystals with a tailored diameter. And so can we use these structures to absorb the light in a better way? Also, can we have these structures to funnel the light inside, or is there some kind of effect that you absorb light in an area that is larger than the physical size of the nanowires? So I'm going to answer this, and this is what led to a good discovery in which we saw that we can save a lot of materials by using these filamentary crystals. So in an experiment to elucidate what happens when you have these filamentary crystals standing up on a substrate, we made this following experiment. So we have a vertical nanowire and we put it in a solution, and the solution is full of fluorophores. And the fluorophores are there for us to map where the light is when we illuminate the structure. And then we go with a confocal microscope and we map the emission. So we use fluorophores that have a very high yield in a certain wavelength, so that every time a photon hits them, they emit light, and they emit light in all directions, so that we can capture it with a confocal microscope. So the experiment, we excite with 633 nanometers, and we collect emission at these other wavelengths, so that there is no interference with the laser. If we simulate this, what we see is that, in fact, the light should couple very well to the nanowire, and we should, the light should also, around the nanowire, should couple there. So we should develop some kind of a black shadow around it, so the light would disappear around the nanowire. When we do the experiment, we see the following. So we go with the confocal microscope and look around. You see that there is a light that is very close to the surface of the nanowire. So these are fluorophores that are very close to the surface of the nanowire. They are not fluorophores inside the nanowire. And it's because the light has coupled into waveguiding modes of the wire that are leaky. So these are leaky modes. So there is some field that goes outside the wire. And that's why it still excites the fluorophores. The intensity is very high because you have concentrated all the light inside the nanowire. You also see that there is a dark region that develops. And this is because the light disappears as soon as it gets into the nanowire. So as long as you go along the length of this filamentary structure, the light gets coupled in, and then the photons disappear and develop this shadow. And you can see here in a cross section how you develop a black shadow around the wire. And this is all photons that have disappeared. And so it tells you that this empty area around is still useful because it allows you to couple the light inside, and therefore you have a very few material that you utilize to absorb the light. Now we then went to apply this into the concept of solar cells. So if you can couple light photons inside the structure and photons that are supposed to be outside, then it means that you can separate the wires quite far away. And so the concept would be that the light couples in, so you have all this affected area that couples into the nanowire, and so you are allowed to separate these wires far apart, and this should allow you to have a reduction in the material use that is very high. So we went to demonstrate first a single wire solar cell. This is a gallium arsenide nanowire. It is obtained on a silicon substrate, so that the substrate is not made of gallium arsenide, because this would be, again, you'd be using a lot of this expensive gallium arsenide. So we have a PN junction, so a highly doped P-type core, an intrinsic shell, and an N-type shell. And then we contact the P-type through the substrate that is very highly doped, and the N-type shell through a top ITO separated with a transparent polymer. The IV curve that you see here is in the dark, and so it's a typical diode behavior which you would expect from the PIN junction. As we illuminate under one sun, we create a photocurrent, and it shows that it works as a solar cell. If you look at the current density here, you will see it's very high. So it's 180 milliamps per square centimeter, and you are in the field of solar cells, you will realize this is extremely high. You know, the best solar cells would have about 40 milliamps per square centimeter. And this is not that this is a very good solar cell. You see the open circuit voltage is good, but it's not like super amazing. Gallium arsenide you would expect to go up to 1 volt. So what happens here is, in fact, we collect much more photons than just the photons that go on top of the nanowire. And so by collecting photons that are around, you are able to increase the photocurrent by a lot. You can then calculate the external quantum efficiency of the same wire standing or lying on a substrate, and you see here the difference. When it's standing, per incident, nominal photon incident on top of the wire, you can generate up to 15 electron hole pairs close to the band gap. That's where you need it the most. Well, when the wire is lying down, you create many less because it collects the light much less efficiency. So this is exactly the same PN junction, just standing or lying. The coupling of the light will vary a lot. And so it shows that really this effect of concentrating the light works. And so what this, and it is about 15 times photons that you collect. And so you can think about how the device would look like. And what comes out is that you should be spacing the nanowires by about 1 micron. And this gives you about 1,000 times savings in materials. And this is very important because gallium arsenide is scarce. And so it means also that the nanowires, because they work under concentration, the VOC can be increased. And so that you can also increase the efficiency if you have a perfect device. Using this concept of absorption cross-section that is much bigger than the cross-section, physical cross-section of the nanowire, we also work on different kinds of multi-junction solar cells, basically having materials of different band gaps next to each other, absorbing different parts of the spectrum. You can look at this paper here where we see that by having an array of nanowires with different compositions, we can get up to 40% efficiency in theory. We didn't demonstrate it experimentally. Now, where we stand today, so similar to the same time that we demonstrated the concept of concentration, self-concentration in standing nanowires, it was the group in Lund that understood the same thing. They understood they need to tailor the diameter and the distance to optimize the light absorption in the devices. And then they demonstrated a device that was very close to 14% efficiency in an array. Later on, also now they have an efficiency about 15.2%. Later on, the group in Amov, they demonstrated that this effect, that you can increase the open circuit voltage by this self-concentration effect, and they reach an efficiency with indium phosphide nanowires of 18%. And so far as I know, this is the maximum efficiency that has been demonstrated to date with nanowires. Now, going to the different topics. So I've shown you how with gallium arsenide, even though it's not ideal from the ecological point of view, you can still save materials, so to bring the material in the other quadrant. Now, I'd like to go to the next quadrant, and I'd like to see what can we do with the material that is a bit farther away in the quadrant. Can we make zinc phosphide a viable absorber for photovoltaics and therefore enable a technology that can be put on every roof? For this, we started a new project, and so we had to buy a new MBE machine and really started from scratch. We calculated also from scratch the phase diagram to know how to get to this phase of zinc phosphide. And you have here the team that started this, and we have recently a new postdoc, Mira Dimitrievska, that has joined us and is helping us a lot with the progress. So with the properties of zinc phosphide, it has the right band gap, about direct band gap around 1.5 electron volts, a very long cadmium diffusion length, an absorption coefficient that is very high, and a tetragonal structure, which means that basically you have difficulties in finding lattice match substrates. So the challenges is it's a very large unique cell, and it also has a very large thermal expansion coefficient. So it's very difficult to grow it in thin films in a traditional manner because you will create dislocations, and also when you cool down from growth, you may create also a lot of cracks. Doping and heterojunctions is still a challenge, but it means we have a lot of work to do. So the strategies we've looked at is starting to grow the structures and the nanoscale, because in this case, you're not dependent on the lattice match with the substrate because of the small area here, and also growing on graphene, because there on graphene, you don't have a covalent bond with the substrate, so it doesn't matter what lattice constant you are, you will just grow. And also with the expansion coefficient, even if your structure expands much faster than the substrate, it just floats on the graphene, so it doesn't really matter, you don't create any cracks. So starting with the growth on graphene, we started tuning the fluxes and the temperature to understand how this material can form on commercial graphene. And so here we use commercial graphene from Graphenia obtained on silicon substrates. And of course, if you grow on graphene, if there is no covalent bond with the atoms that arrive, you will grow nothing because there is no binding. So you rely on commercial graphene where there are some grain boundaries and some defects, and that's where the growth will start and nucleate. And from there, we'll expand, creating some grain. Here you see from some of the initial phases where you see where the crystals start to be created. You will see here, you have here a detail where they show that many of them are oriented in the same direction. So when they merge, they form a single crystal. And here you see a layer. It doesn't look very beautiful. It looks like you wouldn't be able to do a device. But when you look at the optical properties, and this is the optical properties of this material, you see that you have emission, in this case, below the band gap, but it's very strong. And so it gives hope that this material can still be used and absorb as an absorber in the solar cells. Now, moving to the other strategy, we looked at how to create nanowires with this zinc phosphide. I've shown you before that nanowires are good structures for solar energy conversion. So we also looked how we can create zinc phosphide in nanowire form. And we looked at the phase window where we changed the temperature and the 2:5 ratio, and we found the different structures they form in different conditions. So these are the different structures we create. Of course, we prefer the nanowires that are vertical because they're much easier to contact when we create devices. Looking also at the stoichiometry, we found a surprising result. Is even though you have a compound semiconductor with a very defined formula, in fact, we have seen that we are able to change the stoichiometry or the zinc to phosphorus ratio in a quite long range, depending on the growth conditions. And so for us, it means that the zinc probably has different oxidation states in the material. And we were interested in knowing what is the effect of this in the optical properties and if the material is still functional when this happens. So what we see here is cathodoluminescence experiments on the optical properties of this material. So you have all the kinds of structures, so the zigzag, nanowires, the tilted and vertical structures, and all of them luminesce in cathodoluminescence. These are low temperature luminescence. And what you have different emission depending on the structure and also depending on the stoichiometry. So what we see is that even though this is supposed to be a very stable formula, in fact, you can change the zinc to phosphorus ratio quite well with the conditions. And this leads to different absorption rates. And so it opens again the way to change the optoelectronic properties. Moving on, we decided to also use this principle of nucleating the growth in the nanoscale to create the thin film. So we started with a pattern substrate with nanoscale openings to start the growth. And then when it started growing, it creates the facets that are more stable, creating some nanopyramids. And then these nanopyramids will join, forming a thin film that is already textured to collect the light in a much improved way. When we do this, we see is a colored plot where we see the starting of the growth, where you have some nanograins here that join. And even though it doesn't look good at the beginning because you think they are just not coherent. In fact, they turn out to be coherent, and they create these pyramids that then join and form this textured thin film. You can see here in a cross section. In the cross section, we see that even though the nuclei start independently, and they shouldn't be a reason why these pyramids would be single crystalline. In fact, they're single crystalline, and they merge also forming a crystalline structure. And finally, this is the properties. We see that these pyramids exhibit luminescence, and depending on the substrate we use, if it's intrinsic N or P, we have a kind of Schottky behavior or non-ohmic behavior, or more like a p-n junction behavior when we have the junction with an n-type substrate. So this again shows that these layers are p-type, and there is some potential for using them in solar cells. So this brings me to the conclusion, and hopefully I have shown you that so chemistry, material sciences, and physics approaches can help us tackle sustainability on current and future technologies, and nanostructures can provide a way to save resources, and both due to the size, but also to the natural properties, and also because we can fabricate them in much better ways than in thin films. And I have hopefully showed you that these structures provide hope for novel paths on energy conversion in a sustainable manner. So finally, I need to thank the funding, the collaborations, and especially my group, because they're the one doing the hard work. So I'm very thankful that I'm able to work with very nice people. Thank you.
Anna, thank you very much for a very nice talk and beautiful nanostructure that you work with. I think we have a question, if you want to see it in the Q&A panel.
Yeah. So how are these nanowires precisely synthesized with proper separation? And in future, how will you manipulate the diameters? So I guess this is, I'm not sure if this belongs to the 3.5, so the gallium arsenide nanowires or the zinc phosphide. So for the gallium arsenide nanowires, we have a substrate, silicon substrate that is patterned with, so it's oxidized silicon substrate, we nano pattern some holes and the wires start growing there. How we prepare this is key for the success. So there is, we have it in the papers how these holes have to be, the size, and then this determines the initial diameter, and then depending on the growth conditions, we will have them growing fatter or not. And even if they're not fat enough, we can even grow shells afterwards once they are long enough. So we can tune the axial and radial growth very easily with the gallium arsenide. For the zinc phosphide, it is a bit more tricky to control the diameter. So far, we have to play with the growth conditions because we rely on self-assembly. We wanted to grow also on a pattern, to go towards pattern growth of the nanowires, but then we found out this way of creating the thin films from the nanoscale hole. So for the moment, we are not pursuing this path because we think that this nanoscale nucleation of thin films has a much brighter future for the solar cell. So for the moment, we didn't go for controlling the diameter so accurately for the zinc phosphide.
Thank you, and I have another question. Let me see. Okay. You know, we work with perovskite solar cells, and I saw 18% efficiency on your solar cells with nanorods. That's very impressive. How do you compare? I know we should not compare technologies, but I mean, it's very impressive that you have 18% efficiency on these nanorod solar cells. So can you talk about a little bit about that and your expectations in comparison with perovskite solar cell technology?
Yeah. So just to clarify, these were not my results. It was from AMOLF. So it was the group of AMOLF that demonstrated this. So, so technologically, that's also one reason why we're moving to more these nanostructured solar cells. It technologically is very tough. What is tough is not the fabrication of the arrays. I mean, this is now solved. What the toughest thing is the contact scheme. And it's not like, I mean, the people that have the highest efficiency are the groups in the world that have, I mean, the best clean rooms. And you see, like AMOLF, I mean, they were using the clean room of Philips. So they are very advanced in clean room processes. And these are really challenging processes. I think the contacting part with the perovskites is much easier. Then, of course, from these are solar cells that are stable in time as silicon. So you can expect them to work for 30, 40 years. So this is then the stability part is solved. What is not solved is making these contact schemes easy to make and cheap to make. For the moment, this is, in my opinion, not solved.
Okay, thank you very much, Anna. If there is no question, so we thank you very much for your...
I think Sakya has a question.
Oh, Sakya, I'm sorry. I always miss you. I'm sorry. Please go ahead, Sakya.
Thank you so much, Anna, for a very inspiring talk. I have a question regarding, do you have plans to apply this nanostructure approach for OPVs or organic hybrid PVs? You know, this is a concept, you know, about this finger concept that have been, you know, discussed a lot. And or do you know of other groups that are interested in that?
So, I mean, I would be very interested in working with groups that have the expertise of the organic semiconductors to combine the two, either as hybrid solar cell or as also as a tandem solar cell, because one can just match the band gap. So I would be very interested in that. So far I didn't find a group to work together, but I would be very interested. Yeah.
So what do you envision as the light harvesting material, the organic part or the inorganic part?
So that's a good question. It's a thing to discuss. I mean, our materials are very good absorbers.
Yeah.
We have in a recent paper we have shown the zinc phosphide absorbs 10 times more than gallium arsenide, given the same thickness. So it's a very good light absorber. So probably it would be good to have the extraction. So if it would be a type 2 heterostructure, you could use the organic to extract the carriers selectively. So I would probably envision it more like this, but it's to discuss.
Thank you.